All right, so I received another question on exercise 11.1. So this is our human cannonball problem. And specifically, I was asked about part 4. And so in part 4, you're asked to replace the use of fzero with ODE events. So our use of fzero previously was essentially to solve for the time it takes to hit the ground. Because if we're trying to solve for the optimal launch angle, the idea is we change the angle, we compute the distance traveled. Optimal launch angle is going to be the one that gives us the greatest distance traveled when we hit the ground. Okay, so let's flip over to MATLAB. Okay, and so before we take a look at the code, just want to point out one other feature. Okay, so where do I put my head? So I have the code as I received it. We'll take a look at that. But then I also, before I started recording, saved a copy of the event function template from the text. This is just the template directly from the text. Just, get full disclaimer, whenever I need to use ODE events, typically I just copy and paste this template and then update it for the problem of interest, right? I don't remember all these variables or settings I need. I just know where to go to find that template. Okay, so let me bring up the projectile code received. And let's take a look at it and see what we have. Okay. So looking at it, it looks very much like the code from the last debug video. So that's good. It looks like hopefully you watched that and benefited. So it looks like you created a vector of masses, a vector to store the maximum distance traveled and the optimal launch angles. Start with a minimum theta in our search of 15, and then you do our trick of, we loop over masses, find the maximum distance traveled and optimal launch angle for that mass, and then that optimal launch angle becomes the minimum for the next iteration. Good. Okay, and then we plot that. All right, so let's look at through the code first, see if anything stands out, and then get to work. So this helper function, so it looks like it's essentially the same from the last debug video. So the goal here would be for a given mass to solve for, so for a given mass and minimum launch angle to include in our search, we're going to solve for the maximum distance traveled and then the corresponding optimal launch angle. So here's our initial position and velocity. There's our vector of angles we're going to try, going from our minimum up to 50. And we'll use 100 equally spaced points. Initial x component, y component of our velocity. Initial time. A vector to store the distance traveled, right? Because we're going to use that to find, the optimal angle. Looks like here you have options for ODE events. It's underlined because it's not used. So let me just comment that out for now. Since it's not used, we'll assume you're using fzero, and we'll get that working and then update it. Loop over angles. Yeah, so just like the last debug code, you're going to use fzero to solve for the time it takes to hit the ground. That's nested. So when fzero finds the time it hits the ground, it can return, m, which in this case would also include distance traveled. Okay. The one thing we'll need to change is, since I just commented out the options, and it looks like you're not passing options to your ODE 45 call, then it's not going to return these optional variables te and me. Okay, they're not going to be returned because you're not using options, so there are no events as far as ODE 45 is called. Okay, so I'm just going to delete that for now. And in theory, we don't actually need it for this problem, but I'm just going to delete it because there are no events yet, and so that would throw an error and shouldn't solve. So there's our projectile, so our acceleration file that we're using for our ODE 45 call. Acceleration file. All right, one thing that stands out to me here in the acceleration file is you calculate v hat on line 91, but then it's underlined in red, which means you don't use it. And so then if I look at drag, so you have negative CV squared, but you're going to need V hat, right? And so this should be times V hat. So let's put that in parentheses to make it clear. Then let's do times V hat. And so the idea is V hat just gives you the sign of your velocity in both the X and Y direction, because your drag is going to act in the opposite direction. So if my, say, X velocities, it's always going to be positive, so drag is going to be acting in the opposite direction, right? And so that's where the negative sign comes here. Y position, though, or Y velocity, so initially you're going up, so drag's pushing down. Then after you go through your maximum height and you begin to descend, now velocity is going down, so drag's actually pushing you up. So you need V hat, so just multiplied by V hat. All right, so then F drag is a vector. You're dividing by mass, which is a scalar. And so I believe this should actually need to be element-wise, right? It should need to be period divided by mass. Okay. All right, so I'm going to save that. Okay, then I'm going to run it just to make sure the code we're starting with runs. Okay, paste that down here. It's certainly running. My fan's beginning to hum, and we get our plot, angle versus mass. Again, this looks just like our first debug video. Great. So we have that working. Now let's see how we would use ODE events. Okay, and I'm going to try one more thing. So I made a comment to try time it. So before I forget and we update the code, let me try it. So MATLAB has this built-in function time it, and time it expects as an argument a function with no inputs. So I'm going to give it just our function handle because it has no inputs. And what time it will do is it'll run the code several times and it'll compute the average execution time. Looks like I messed up the use of time it. Okay. Doesn't actually return anything. So we'll go ahead and delete res. Okay, so there's apparently the first time it runs. Now ideally, you would just save a copy of this code. I should probably do that, but I'm just going to edit it just to confirm it works. Now we did include some tricks in our code to make it pretty efficient. So this code takes 3.45 seconds to run on my computer, right? So it's pretty fast. And part is those tricks in terms of that we implemented in terms of what do you call it, min angle, the min theta that we're going to search, and then cutting out of our for loop early. All right, so event function I'm eventually copy and paste, but I'm going to leave it for now until we get the position just right. Okay, and so what I'm going to do is I'm going to maximize this animal. Okay, and so all I'm going to do is I'm going to go down to our for loop. Okay, actually where do you have options? We have options here. Okay, so I'm going to uncomment out options. Okay, so in terms of the position of my event function, okay, so it needs to be so that, let's see, options is in my top function, right? So options is in this helper function, this projectile model angle. And so that helper needs to be able to see my event function. So in this case, it could just be in parallel since it just needs to be able to call it. Okay, so it needs to be in the same level or nested in that function that it's being called from. Okay, so it could be parallel. So I'm just going to paste it down here. So we'll call it event function. It can have inputs of T and W, right? That's good. All right. In theory, could copy the documentation too, right? But it won't bother here. Okay. All right. So event function is going to have the same inputs as my rate function, right? Projectile, so T and W. Okay, got it. So what we're trying to do is we're trying to solve for when the height is 0. Okay, our event's going to be when the height is 0. So even if I just look at projectile, okay, so if I partially unpacked W, the first two elements are going to be the X and Y position, right? And so, this example is already kind of set up for, projectile problem. Okay, so I'm going to extract my Y position is going to be W2. Okay, my event will be when my Y position is equal to 0. So I can just make my event, my Y position, because it's just like fzero, right? So an event is when that function is equal to 0. Right, so in this case, my event is going to be when py is equal to 0. So that's good. Is terminal. Okay, so remember, is terminal is a logical variable. Okay, so 1 means true, right? It's a terminal event. So when that event happens, stop. If you made is terminal 0, that's false. It's not a terminal event. So that when that event happens, keep integrating. Right, so we'll just keep it as 1. So far we're good, right? This is the exact same example that we needed in the chapter. And then direction. It's not essential, but you can use the direction to specify if, in this case, py is going to be increasing when your event happens, decreasing when your event happens. So that's plus 1 or negative 1, or you could just use 0. 0 means I don't care, right? It doesn't matter if it's increasing or decreasing. In this case, since we know it'll be decreasing, we can just keep it as negative 1. Okay, so I've got event function. Let's make sure we call it up here. Event function. I'm going to put the underscore so I use the same name. Okay, and so I should see event function go away there. Okay, so now I've created this variable options. All right, and so then what's going to change is, the purpose here, okay, of projectile solve is we're just using fzero to keep iterating on the value of t until it finds the t, at which point it hits the ground. Okay, at which point that's my solution, that's my trajectory. I'm going to use that matrix M of x and y position and velocity in my x and y direction. Okay, so instead of f0, we're just going to use ODE Events. And so what I'm going to do, okay, I'm going to delete X impact. Actually, let me comment it out so you can see what we used to have, just like we used to have it here. Okay, so now I'm going to solve my ODE using ODE Events. Okay, so basically I'm just going to copy and paste your ODE 45 call here, okay? But after my initial conditions, I now need to give the additional optional variable options, okay? So now options is as I've defined up here. And then the one thing I need to do is this time range, okay? So t naught is 0, okay? So that's known. T is unknown, right? And in fact, that's what I'm actually trying to solve for, right? The time it takes to hit the ground, right? I want to solve until it hits the ground. I don't know what t is, okay? And so basically you just need to make t some big number. You need to make, t some number, how do I say this? So ODE 45, so based on my event function, I have this terminal event, at which point I will stop integrating when my y position is 0, okay? So it's a matter of what will come first. If I were to specify a time of 1, okay? So this would say integrate from time 0 to 1. So my ODE 45 call will stop integrating at a time of 1 or when I have a terminal event when my y position is 0. Right? It's an OR event of what kills ODE 45. So what I want to do then is I just want to make my time big. It would have been useful to look at my other code to see what sort of times we were solving for. But basically just make time some big things. So let me make time 10,000 seconds, right? That seems abnormally high, right? And the goal is to make it some time that I'll never actually get to, right? That I'll have a terminal event I hit the ground before I ever get to that time. All right, so it just needs to be some big value. But that should be it, because as long as that time's big enough that I'm going to hit the ground before I get to it, okay, subject to options, ODE 45 will stop integrating when I hit the ground. Okay, and so you could add those extra optional arguments, the time of your event, and the position of your event. But in this case, it really doesn't even matter, because it's just going to stop integrating when it hits the ground. And so then we can just keep all of this exactly the same. So I'm going to save it. Okay, and all I did is comment out your projectile solve, in which you use fzero. Okay, so that's been commented out. And then right above my for loop, I put your options definition back in there. Move my ODE 45 call from fzero, where I had it before, or my error function where I had it before, up into my for loop. Added the extra optional options, and then I had copied and pasted that event function directly from the chapter down here. Okay, so if we give it a try, cross our fingers, right, it runs, right, and that looks exactly the same, right, which is good. If we were to time it, all right, so difference, so that took 0.3264 seconds to run, right? Time it might seem a little longer because it's actually running multiple times to make sure there isn't variation in time from run to run. But that's a factor of 10 savings. So even with all our little efficiency improvements, it's still a factor of 10 improvement by using ODE events. So that's it. So hopefully, see, it's really not all that much you need to change. It's rather small. It's rather minute. It's just a matter of doing. And then the one disclaimer, making the problem statement is if you were to look at the actual numerical values that you calculated. So say if you were to return those distance traveled and optimal angles, you might find some small numerical differences in what fzero returns and ODE events returns. And in fact, if you were to do that, and you were to look at, say, when the event happens, you might find that y position isn't exactly 0, right? There might be some slight numerical inaccuracies, right? But typically, for all intents and purposes, it's good enough. If you ever need ODE events to achieve a more accurate result, have a look at the documentation, and you could also change the settings of ODE 45 to achieve its precision. Okay, but for the purpose of this problem, there you go.